Thank you, Kejin. So I'm going to talk about, I'm hoping that you didn't have a buildability fatigue yet. And if you had, apologies for that. So we're going to talk about early age response of 3D printed systems evaluated using digital image correlation. But before I get to digital image correlation, we need to do a little bit of background. I'll skip all of these things. We just don't need any of those. Previous speakers have really educated you on this, so I can skip all of that. So what we need is, if I have to have a model for buildability, I need to understand what's the fundamental physics that goes behind and what are the mechanical evolution of properties that happens. So basically what we are going to look at is considering material property development, stepwise stress growth, and then verifying multiple print geometries of where it's coming back. And then we'll do digital image correlation of fresh printed samples. Okay. So three things that you have to look at if you have to formulate an analytical model is the material characteristics, the stress growth, and the failure modes. And you've seen buckling failure, yielding, etc. So if you're looking at material characteristics, we are looking at a bilinear stress strain model, and I'll tell you why bilinear. We are looking at stress growth in different layers, and then independent or combined modes of failures, the elastic buckling, elastoplastic buckling, plastic crippling, plastic yield. Again, these four based on several different printing tests that we've done and kind of identified what the likely methods are. And you can simplify it to be a stepwise stress growth. So basically the idea is that with adding layers, the stress on the bottom layer keeps increasing, and you use that stress development per layer as an indicator of what goes into the stress growth model. I'll talk to you about what happens next. So we did a bilinear stress strain curve. So we talk about, again, this is by doing plastic response at extremely slow deformation rates, with extremely slow loading, so that you're not missing out what is happening when deformation happens in very plastic mixes. So I call this an elastic yield stress where there is a kink. This, I call it a plastic yield stress. It's still a secondary elastic stress, not really plastic, but for a lack of better word and to reduce confusion, we call it plastic yield stress. So you have two different distinct points in the stress strain curve and correspondingly two different slopes of it. And then it's a nonlinear plastic regime. We can just ignore about that for the time being. So if I have only 3 layers built up, just as an example, I'm saying that all the stress in this lowest layer is less than this elastic limit because there is not so much of load. But if I keep building up, I'm going to see these layers and these layers getting into this zone. So that is the way in which we qualified. I'll show you the test method that we have done. And then there is a whole procedure to convert all the theoretical information and the experimental information into calculation of layer heights. But like I said, you have an elastic buckling, a plastic buckling, a crippling, and an effective failure length. So here are the 4 mixtures that we did. Inconsequential in the scheme of things, everything behaves similarly. We are not doing a mixture-specific work here. It's a method-specific approach at this point. So again, just to show that these are mixtures that we have done with 30% replacement of cement with limestone, with superplasticizer, fly ash limestone, and a lightweight aggregate mix instead of a normal weight aggregate, just to show the difference in stress development and the self-weight effects on buildability. Okay, so the experiments, I know why this picture is showing up at the corner, but what we did was to print layers of samples and then carefully extrude a cylindrical sample, make sure that it's leveled nicely, and then do a green compression test at extremely slow stress strain rates to extract the elastic and plastic stresses and moduli, which I just showed, to predict different failure heights. And at the same time, print walls and hollow cylinders at different times after mixing to see how buildability is evolving with time. So here are the stress strain rates and all the parameters that we have extracted, the yield stress, the elastic yield stress in the modulus, and the plastic yield stress in the modulus, just 4 of those parameters for different mixes at different times after mixing. So printed at half an hour, 1 hour, 1.5 hours, 2 hours after mixing. And then, of course, you've seen this in previous presentations, thixotropy, yield stress growth, and a standard structuration factor. So I'll skip that as well in the interest of time. So we defined failure when no more layers could be printed because of significant geometric deformation and or collapse. For example, here, I still can print a few layers, but you can see significant geometric deformation. This is considered failure. But if that doesn't happen, that's not considered failure. We made wall and hollow cylinder prints because they have different geometry, different elastic modulus, different kinds of moments of inertia to precipitate different types of failure when you start building up. So everything is based on theoretical failure curves from 30 minutes until 2 hours. So if I look at that, just to give you a few examples, all the green dots are the experimental heights at failure, and the lines are different models that I showed earlier predicting the failure heights. And you can see that for wall prints, you can see here that a crippling height or even a buckling failure is what is happening, what is dominating, especially after about 1 hour or so. Same thing with here also, where you have here it's a plastic height, that is plastic failure that's dominating for a different set of mixes. And then when you get to a fly ash limestone mix, which did not have enough of strength development, it was a pretty weak mix. You can see there is a little bit of transition from one failure mode to other as we go through. But we'll talk about this a little bit. So failure heights predicted by buckling or crippling curves for walls. Plastic failure curve is independent of the print geometry for both walls and cylinders. You could see that. Buckling, crippling depend on the geometry of the section because of the moment of inertia influence. For cylinder prints, as failure modes change with time, there is a crossover sometimes. But the idea is that using any of these established models and the parameters extracted from a very simple green compressive test, carefully done though, to get the plastic and elastic parameters, you can actually predict the failure heights fairly nicely for the cases that we talked about. Now the question is, okay, I have predicted it, I have 4 more minutes. Good. So I've predicted this. Now, is there a way to non-destructively do this or to understand what is happening in the system? So far, we use the idea of stresses. We are moving on to the idea of strains now by doing digital image correlation. So what we did was a slightly modified way where you initially print 4 layers of your concrete, speckle it, make sure that you can make measurements using digital image correlation on that, and then build up layers on top of that, and then see what the relative displacement of the bottom layers are after you have built these 4 layers. And like in a previous presentation, you showed the bottommost layer is probably not the real good indicator. So we mostly use layer 2 as an indicator of what is happening. And you see here the stepwise stress buildup rate. You can see a similar stress-wise strain buildup rate. And what you see here are the layers being the vertical non-print nozzle travel. So if the if the nozzle prints and then it lifts up and moving, there's a little bit of dip that you're seeing in between those layers. So this is layer 5, 6, 7, and 8 after the first 4 layers are printed. And here you're seeing the vertical displacement profile. You see here the next layer is being printed. You see here increased displacement because the nozzle is pushing under it. This is the 3 additional layers are printed. It's a little unclear because of the light, but if you look closely, you can see 3 more layers on top of that, and the displacement of the bottom 4 layers when 3 more layers are printed. This is the increased vertical displacement that you see before failure initiation. This is right when the print fails and collapse. This is no specific localized displacement. Here you see a crippling failure. You see here, these are the 4 spectral layers, and there's a rotation around that plane with an out-of-plane displacement that actually you can see from this picture. And this is more details of those out-of-plane displacement. So the strain rates as failure indicators is what we are looking at. And simply what we've done is the fact that if you look at the vertical compressive strain as a function of time, the vertical compressive strain changes. You see here, there's a significant increase in vertical compressive strain with printing time. We use that location or that time or the number of layers printed at that time as an indicator of initiation of failure. Similarly, for out-of-plane failure, you will see a reduction in strain because the print, if you have a wall print, is coming forward and into the plane of your camera. So you see a drop in strain as measured. That is an indication of a buckling failure. So you can use those, whether a positive increase in strain or a reduction in strain, as indicators of initiation. Now, this is happening much before you actually see the print fail. So this is way ahead of time, which I'll show in a minute. So here are a few examples of the vertical compressive strain as a function of printing time for a certain mix. Okay, so if you look at critical and initiation heights, these are the critical or visible failure heights, which are based on the previous set of slides that I showed based on the analytical models that we did. And these are failure initiation heights based on digital image correlation. You see that there is one-to-one correlation for a couple of mixes here, but when you get to the lightweight mixes, you see that your visible failure height is much larger than the initiation height, which means for lightweight mixes, you're able to capture initiation much more because of the differences in the characteristics of the lightweight mix. The idea is that you have lower superimposed stresses in those mixes. So with strains, you can much effectively capture it before stresses reach a peak stress. There is a stress reduction of about 1 kilopascal in the bottommost layer, even after building up 23 layers because of the reduced self-weight of the mixes. And then there's a better rate of stiffness increase, 3.1 kilopascal per minute base, as opposed to 1.8. So, and just to give you failure envelopes, if I can put all of those together and create failure envelopes, and then look at the failure mechanism as a function of time. So very early plastic collapse for this mix is a normal mortar mix with 30% limestone. You can see beyond this is crippling failure. These are all initiation times. This is the actual failure, initiation heights. This is the actual failure heights. Not much of difference if you see these mixes, but when I have lightweight mixes, you see the difference in the initiation time. And again, the predictions are fairly good. The initiation time versus the final failure time. So you can see that this is the additional height that the wall can be built before visual collapse. For very normal weight mixes, you don't have that kind of a difference, but DIC is able to very nicely capture that strain difference. So this is talking about when you have reduction in strains because of the reduction in weight of the mixes, and that's quite well captured. And you have a really large zone that you have here. So to conclude, a 30-minute presentation compressed into 11.5 minutes talk. An analytical model accounts for failure mechanisms to predict buildability. We have an approach based on cumulative vertical strength. For this, for information, these are published papers. I can send you that information if you need more information. Vertical strain rate buildup is indicative of stiffness development when printed at different times. DIC as a real-time method to monitor property changes. Again, when I say real-time, it's not that you can take DIC and do it right in print, but qualify mixes ahead of time and look at what different mixes would do. And vertical strain profiles provide decent indications of failure rates. Thank you very much.